Hello, this is Coach Meinbauer from AP Calculus. This was an AB and BC set sent out. We're going to work on limits with laws in algebraic. So let's go ahead and get started here. There are some basic limits that you do need to know and to understand here up in this part. So if you have a limit as x approaches a, and that is a constant value, you're going to get that same constant value. Right below that, you have a limit as x approaches a of just x. We just plug in right away. I do real quickly want to draw out what this 1 over x looks like. Well, that's what they say is a little thick. Let's see if I can get this. Oh, there we go. So we got asymptotes right here on the x and the y axes. So this is what 1 over x looks like. And you can clearly see as we go just left of 0, we're approaching negative infinity. If we go just right of 0, we're approaching positive infinity. There are some limit laws we need to know. You can kind of read up there. If we have the limit as x approaches a of f of x, we get L sub 1, and limit as x approaches a of g of x is L sub 2. If we were to add those two limits together inside of our argument, you can actually take them outside the argument and just add up the limit as x approaches a of f, and then add that to limit as x approaches a of g. You can do that same thing for subtraction and multiplication. Division is slightly tricky. You got to make sure that L sub 2 is not 0. If you do get a 0 on the denominator, it does not exist because you cannot divide by 0. And we do have a square root 1 here. If it is a square root, then that limit has to be greater than 0. If it's like a cubed or a fifth root and that end value is odd, then it doesn't matter if the limit is positive or not. All right. We'll go through this first example. It just says use limit laws to find this limit right here. When it says use limit laws, you do have to use one line worth of limit laws. So I'm going to go through and use our addition and subtraction limit laws as we go through this problem. So this can rewrite as the limit as x approaches 5 of x squared minus limit as x approaches 5 of 4x plus limit x approaches 5 of 3. So I just used my limit laws. So now if I plug in directly, I'm going to get 25 minus 20 plus 3 gives me an answer of 8. If our denominator of our limit is ever 0 and our numerator is not, so that means we are of the form number over 0, then that's going to provide us with 3 situations. The limit can be infinity, negative infinity, or does not exist. In order for the limit to be negative infinity, both the right and the left from where we're going up the argument has to approach negative infinity. Same thing with positive infinity. But really, anything that is infinite does not exist anyway, but sometimes we want to know if we do approach infinity or not when we start getting to composition functions, and that can get kind of fun. So let's go ahead and go down here. Let's look at the limits of when numerators and denominators are 0. So it's in the form of 0 over 0. We do not want to write equals 0 over 0. That will provide us with a linkage error. And we cannot do that because if you get an answer on the first one of 4 and you say that the limit equals 4 and the limit's equal to 0 over 0, that's a linkage error, so we do not want to do that. Also, do not use arrows. That's no good as well. So for the first one right here, you can clearly see that our numerator will get us a 0. Our denominator get us a 0. So what we want to do here is we want to factor this. So we're going to limit as x approaches 2 of x plus 2, x minus 2, all over x minus 2. So we're going to have the term on the top and bottom cancel out for x minus 2, and we're left with just the limit as x approaches 2 of x plus 2. And now we can do a direct plug-in of 2 plus 2, which is 4. For the next one here, this is one that we really can't factor. It has unusual factoring if you do go through with the factoring. So because we have the square roots, we do want to multiply by the conjugate so that we can manipulate this. Because if you do plug in a 1 in the numerator, you get 0. In the denominator, you do get 0 as well. So the conjugate is going to be square root of x plus 1. We just changed the sign between the square roots. It doesn't matter if it's the denominator or numerator. It doesn't matter if it's even 1 minus root x. We would just change just the sign in between into positives. When we do this, we want to keep our term in the numerator separate. We don't want to distribute that all the way through because we want to cancel. Now, I will distribute the bottom because that's the whole point of multiplying by the conjugate. And so we can manipulate this to turn into an x minus 1, which does cancel. And we get the limit as x approaches 1 of root x plus 1. Plug in a 1, you're going to get 1 plus 1, which is 2. So if you notice right here, I'm going to keep writing limits as long as I still have variables. As soon as I plug into that variable, I can no longer write limits. Now let's go ahead and talk about some piecewise functions here. A couple of ways to do it is you can find one-sided limits or you can graph. I prefer not to graph because the AP exam doesn't ask you to graph. So I like to just go ahead and find the one-sided limits. But before we get to that bottom one, I do want to add an example. Let's go ahead and find the limit as x approaches 3 of f of x. So let's go ahead and add this example. And now we'll go ahead and solve through this example. So for piecewise functions, I want to look at each piece that is adjacent to 3. I want to look at the left side of 3, the right side of 3. And if they match up, that's my limit. If they don't match up, we have DNE. So for this one right here, as we approach 3, I want to look at 3 to the left. Now, of this piecewise function, you have to think about which piece is 3 to the left. Well, I'm looking at the middle one right here because those gives me values between -2 and 3. And since 3 is where the pieces break off, we're looking at just left of 3, which would be the x squared minus 5. So I'm going to substitute that in for my f of x. And that's going to give me 9 minus 5, which is 4. Go ahead and look at the right side of 3, which is going to be the bottom piece. So I'm going to go ahead and substitute that f of x in, or the root x plus 13 in for the f of x. Which is going to give me root 16, which is 4. Since I do have those two match from the left and from the right, this does actually equal 4. So I'm good to go there. That one worked out very nicely. Let's see if this next one does. Let's go ahead and define the limit as x approaches -2. So let's go ahead and look at the limit as x approaches -2 from the left. If we look at our piecewise function here, that's going to be our top piece, which is 1 over x plus 2. Now, in this situation, we will get 1 over 0, so we cannot have that. So we have to look at what this looks like. Well, luckily, this is a graph that we can sketch here. We do have a vertical asymptote at -2. This is something that's super easy to sketch. You just look at 1 over x, you're going to shift everything left 2. So when I do that, you can see in my picture right here, this is 1 over x plus 2. And I'm looking at just 2 to the left of this. If I look at just 2 to the left, that is approaching -infinity. That does not exist, so I do know this limit does not exist, but I do want to investigate further in case both of these are -infinity. And it's just a good skill to have so that when we have composition functions, then we can find these limits a little bit better. So let's go ahead and look at the right side now and figure out what piece to use for that one. What piece should we use? If you said the middle one, you're correct. We're going to use the middle piece there, which is x squared minus 5. If you do plug in a -2 there, you're going to end up with -1. So those are not equal. So this is going to be a DNE. So this limit does not exist. And I'm going to kind of just squeeze it in because all that stuff is true. Again, those do not equal. So I'm done there. And that is going to wrap up our lesson here for limits using laws and algebraic.